Welcome. So, today we are going to get you introduced to convolutional autoencoders, and as you have done in the earlier lectures on just connecting down fully connected autoencoders, where you had a bunch of neurons on which you had your input image as in a batch or on maybe the whole image which goes through it, and then it connects down via all of these hidden layers, and the end terminal over there was going to reconstruct your original image, and your cost functions were defined in a way which is trying to minimize the mean square error between whatever is reconstructed and what was given down on the input side of it. Now, the whole purpose of this autoencoder was to learn representations which can encode the image in its own best possible way, and that would have resulted in a nature of features and a set of features which are hierarchically connected across the depth of the network, which can be used for classification purposes. And this definitely gives you a edge over all the other methods in which you can use an unsupervised training mechanism in order to actually learn down features, and then all of these features which are learned down in an unsupervised manner can be used for initializing a fully connected network in order to do your image classification as an end-to-end pipeline. Now, while we had done all of these once in the first month, and then subsequently we went over to understanding convolutional networks. So, in convolutional networks, one thing which we are doing is you needed a large corpus of data which is already annotated, such that over here, while you are back propagating your errors caused by misclassification, your new features are getting learned, and these features now which are getting learned are in terms of convolutional kernels which appear across the hierarchy. Now, the question which does raise to your mind at that point of time is, can we not have a mechanism for actually learning these features in an unsupervised manner as well, and that would be of a huge application as well as an immense contribution to a field where you have less amount of annotated data for classification learning, while you can have an ample amount of unannotated data. So, which is not labeled, but you have just a bunch of images over there for all the objects which can ever occur. And convolutional autoencoders are basically an answer to this kind of a mechanism. So, where we go down is what you had seen in the earlier lecture, was where we introduced you to a convolutional autoencoder in the form of how convolutional connections are made down, and then it directly connects down to a fully connected layer in terms of an autoencoder, and then you have the rest part of it, which is your decoder block, and that will be making use of either a upsampling operator or an unpooling operator or something even called as a deconvolution operator, as we had introduced. So, today I am going to write down one very basic simple code in order to do all of this part. So, we will have a convolutional part of the encoder, we will have a fully connected part of the encoder, then similarly goes down as a fully connected part of the decoder and a convolutional part of the decoder. So, without much wait, let us get into what this is doing. So, as in with all of our earlier parts, we just end up loading down the necessary libraries which come down over here. So, let us do a simple run over these libraries. So, once your libraries are loaded, then you have your data which is coming down. Now, for the data which we are using, I choose to use down just CFAR over here, the 10 class classification problem data which we have used in the earlier lecture while trying to do it with LeNet as well. So, there we had modified LeNet in order to take in color images, and all the color images which were there were from CFAR. And so, quite contrary, here what we are going to use is, although all of these data does have its training labels in terms of classification associated with it, but we are not going to make use of that. We are just going to make use of the image data itself. So, the labels over here as such are of no use, it is just the image which is going to be used over here. Now, for batch sizes, we use a batch size of larger size over here, it is 2000 images which goes into one single batch. So, let us just get this part running, and once that does, we check in as usual for our GPU availability. So, my GPU is available, and that is great. So, now I am done with my initial part of it in terms of just taking down my data and then getting my stuff initialized. Now, the next part is I will have to define my convolutional autoencoder architecture over here. Now, if you go through this model over here, what it tries to do is I have 4 different blocks in which the whole thing is divided. One is called as a convolutional encoder. The next part is a fully connected part of the encoder which succeeds the convolutional operations within an encoder. Following that, I have a fully connected part of the decoder, and then I have a convolutional part of the decoder as well. So, let us go down how it is defined now. So, on my convolutional part of the encoder, It's basically the first part is a 2D convolution. Now, what it takes in is 3 channel input, because you have your RGB image which is coming down on the input side over there, and then it maps it down to 64 output channels. So, the total number of convolution kernels which you will be having in this first layer is 64. That is the total number of unique channels which it aspires to map it down to. Each of the kernels which we use is a 3x3 kernel, not a 5x5 or any of them. We do a convolution which is a strided convolution. So, that means that necessarily the size of the result over here is going to be smaller than the size of what you had if you were just doing with a normal stride of 1. Okay. So, this is something similar to as whatever size you would have achieved if you had a stride of 1 convolution succeeded by another max pooling with a 2x2 and a stride of 2. So, we just merge all of them together, though functionally it is different, as we had learned in the earlier lecture as well. So, functionally there are going to be certain differences coming down, but this is just a faster way of computing it out and reducing the total number of compute layers over there. And finally, there is a padding available. So, let us just, and then the padding over here is just with a padding of 1 which is present. So, that is like a 0 padding at the periphery over there in order to match it down. Now, all of this is done from the perspective of your calculation, which says that your output width is equal to input width minus the size of the kernel plus twice the padding which you are giving divided by the stride which comes down plus 1. Okay. So, if your input over here is 32 cross 32, then what comes down is that your 32 cross 32 minus my kernel size, which is 3, plus my padding, which is plus twice of my padding, which makes it 2. So, it becomes 32 minus 3 plus 2 over there. So, it becomes 32 minus it becomes 32 minus 3, which makes it 29, and then I do a plus 1 over there, which makes it 28, and that whole thing divided down by my stride of 2. So, that brings it down into a 14 cross 14 sized over there. Now, following that, I have a leaky ReLU nonlinear transfer function given down over there. So, I could have used down a standard ReLU, but however, what we wanted to do was on the negative side of it. If your values are coming down negative, then we still try to preserve some sort of a gradient and not just make down the gradient and response everything over there 0. So, that would technically, for any error which is negative, it's just not going to back propagate any part of that error over there. So, a leaky ReLU helps me to do that with a leak factor of 0.1 kept down. Now, these are personal choices and then nothing beyond that. The more experience you get, you can choose it out, but as of now it is just a heuristically chosen out value. The next layer over there is again a convolution layer which maps down from 64 channels on to 128 channels. So, there are 128 unique kernels, and then you have your kernel size of 3 cross 3 the same way, and then a padding or a stride of 2 and a padding of 1. And then it keeps on going down, and the final part is where from 128 channels you again connect down to 128 channels. Now, over here, by the time you actually reach down this linear part over there, what you have is 128 channels are what corresponds over there. This through this whole transformation over there, you end up getting a smaller matrix of size of 4 cross 4. So, the total number of neurons which are present within this whole volume over there is basically 128 into 4 into 4, and that is the total number of neurons which will get connected in a linear fashion or a fully connected fashion to 1024 neurons, and following that you again have a transfer function which is a leaky ReLU. Now, this completes your part of the autoencoder. So, the like hidden layer which is shared between the encoder and the decoder units over there has just 1024 neurons present over there. Now, these 1024 neurons are now being passed on to my decoder unit. So, what I do on the first part is 1024 neurons, they will just blow up to the total number of neurons, which is equal to 128 into 4 into 4, which is the same as over here. So, this kind of an encoder decoder is symmetrical as it appears over there. Now, following down my transfer function over there, then I start converting all of this onto my convolutional block. Now, since my view or linearization and then repacking is not part of my architecture, but they are just operations which I do on the data. So, that is something which will be defined in my forward function. Now, let us look into the decoder part of it. Now, in the decoder, it is quite symmetric to how it was going down in the encoder part as well. So, in the encoder, you had 128 channels which connect down to 128 channels. So, it is the same thing which comes down, except for this output number of channels is what will correspond to the input number of channels, and this input number of channels over here on the encoder is what will correspond to the output number of channels in the decoder. Your kernel sizes are still 3 cross 3, and your stride which you are using is of 1 and a padding of 1. The whole reason being that over here when I do a stride of 1 and a padding of 1, I am going to retain object of the same size. Okay. Now, whatever was the size coming out over here, so here basically it was a 4 cross 4, and that is what comes down over here as a result as well. Now, that 4 cross 4 sized one which has 128 channels is what gets mapped out over there. Then you do a leaky ReLU, and then you do an upsample. Now, this upsampling over here is just an interpolation upsampling which is taking place. Now, this interpolation will convert this 128 into 4 into 4 size thing onto a 128 into 8 into 8 sized. Okay. And that is something which matches the output which can be fed down to this particular which is sort of symmetrically fed down to this particular earlier layer, and that is what I am going down. So, over here I am going to convert 128 channels onto 64 channels, that matches on my encoder size the symmetrical value. So, you need to keep in mind that whatever is the kind of number of channels and the size on the encoder side is it is just going to revert it in the same way in the decoder side as well. So, finally, when I get down from my last layer over there, so in the last layer I just have a value which is equal to 3 channels, and this output over here is going to be 32 cross 32. Okay. Now, this is about my definition of the architecture. Now, when I do a feed forward, what I am going to do is first I am going to just feed it through the autoencoder through the encoder block or the convolutional encoder block over here. Once it comes down from there, I need to linearize each of them, and that is by using the view function, which is to cast all the neurons into one single linear layer. Then from there it feeds through the encoder, from there it feeds through the decoder, the fully connected encoder and decoder. Now, once I am over here, there is just a bunch of linear neurons which have to be undone and again converted onto my vector space of 128 cross 4 cross 4, and that is what I am doing over here. Now, once that is done, you can pass down this 128 cross 4 cross 4 sized tensor onto your convolutional decoder block over there. And once I come down over here, here I see that my output size is the same as that input which I had provided over here. Now, once this is done, I can define my network, and then if my GPU is available, which for me is there, then I can convert it to CUDA and typecast it out. And then so this is just for printing the network, and since I want to look into what is the kind of weight change which has happened over here, so I would just be copying down my weights and keeping it down. So, let us execute this part and then see what comes out. So, you have your total autoencoder which is defined like this. So, the first part is your convolutional encoder which has all convolutional connections and your transfers in terms of a leaky ReLU. Then you have your fully connected part over there in terms of a sequential part of the encoder. Then you have your fully connected part of the decoder, and subsequent to that you have your convolutional part of the decoder present over here, and this maps down pretty much symmetrically one to the other one. So, once this network is defined for me, so let us get on to training down this autoencoder. So, what I choose over here is to train it over 5 epochs. I have my loss function which is MSE loss function, because this is not a classification problem I am solving in any way. I am just trying to solve down regression kind of a problem. It is just trying to encode the image in itself. So, you just use an MSE loss over there, and again going down the best by the best of the optimizations we have at the current stage, and that is on Adam. So, let us keep this one running because it might take some time to run it while I go through the codes. Now, over here what I do inside is I set my epoch counter running over here, which runs over 5 iterations or 5 epochs, and within each epoch it is going to load down my batch of the data, which is 2000 samples as I had set in the earlier case. And from there what I do is basically look if there is a GPU available, and since my model is converted onto the GPU, so I need to actually get my data also converted onto my CUDA. So, this is where my inputs get converted over there. Now, following that what I do is I set my gradients in the optimizer as 0, and then I just feed my inputs to the network such that I get my outputs. Okay. Now, on my criterion function over here, since my loss or the cost function which I was going to use is an MSE loss function, which basically tries to look into minimizing the error between whatever is the input and what comes down on the output side of it. So, for that reason the argument which goes into my criterion over here is just the outputs which come over here, and the reference In the earlier case when you were doing classification, so these used to be labels, but for me these are my input values over there. Then once my loss is calculated, I need to find out nabla of loss or the gradient of the loss. So once that's done, then I do my optimizer dot step, which is to iterate, backpropagate the whole gradient through the network in order to do an error backpropagation, and then I just do a accumulation of the loss as it keeps on going over the number of batches which goes down. Now with this, what I do is technically take down an average loss per epoch, and so my batch size over there was 2000. So what I am going to do is basically 60,000 are the total number of samples present, and each batch taking down 2000 samples over there. So it ends up being just 30 number of batches which will be present when I am trying to do an update per epoch. So I just take an average over that, and that's the average loss per epoch, and then I just keep on saving it out and do a timer, and then finally it's to plot down what the loss looks like. So if you look over here, it takes down about roughly 25 seconds to run it down. We just ran it for 5 iterations over there, and this is what comes down on the loss side over there. So it started with an MSE loss somewhere around of 0.14, went down to a loss of 0.025. So there was good amount of 1 point of decimal loss coming down. However, it hasn't yet reached saturation. So please keep on running over a longer duration of time, or you can even put down learning rate update rules over there to come down to a much more conversion. However, the interesting part is actually to look down into the visualization, and this is what we have been doing for the last few lectures. So let's get down. So what I have is just a simple definition of the function to get all my weights and visualized it out, and since initially I had just copied down my weights and kept it, so I am going to use my initial weights. So what I do over here is when the network is completely defined, then I make one effort to copy down all my initialization weights or the initialized weights, which are just random initialized over all the kernels which are present over there. Now that helps me in a significant way, because now I am quite prepared in order to look down what happens after the whole training process is over. Now once the whole training process is over, over here after defining this function, what I do is actually copy down all the weights which have been trained, and then my next part is to actually look into what is the difference of the weights, which gives me an idea of how much each weight over there has been updated within each of the kernels. Now having done that, the next part is that your weights can exist either on the CPU or on the GPU, but based on like where you are executing. If you have a GPU available, then it polls it automatically and goes down onto the GPU in order to do it. Now it would just need a typecasting over there, because the rest of the functions for displaying out and showing out the weights, they are what exist on the CPU and not on the GPU. So that's the whole purpose of doing this typecast over here. And then finally we just use a visualization tool in order to see this out. Okay. So let's look into what it goes. So my initial weights are something which looks like this. Okay. Now you need to keep something in mind that we had actually created a model. So if you look into this model over here, and the first layer, which is connecting down any input which comes down into 3 channel into 64 such kernels over there. And then since it's a 3 channel input, so over there my convolutional kernel is of the size of 3 cross 3 cross 3. My 3 cross 3 is this spatial spread over there, and the number of channels is also 3. Okay. So this is technically as if a 3 cross 3 RGB matrix is what we are going to look down into, and there will be 64 of them, those unique numbers. Now let's come down into the visualization. So if you go over here, then the matrix which it forms has 1, 2, 3, 4, 5, 6, 7, 8 number of kernels on this axis. On the other side also you will be seeing down that there are 8 number of rows which come down, and that together makes it a 64 number of kernels which are visualized, and each is a 3 cross 3 in spatial spread and has 3 channels, and that is why you get your colored visualization coming down over here, and that is quite conformal to, since we have the input in terms of a color image itself. Okay. Now these were the weights at the initial part of it, and then once you have trained out the whole process, then you get down your weights which look down quite similar to this one. Okay. Now for most of you it might not even make sense, because it looks as if there hasn't been much of a change. And now if you look down into your weight update, then you can pretty much make up that these updates which have happened over here are sort of like which appear more of scalar in nature, like whatever was the initial randomization, there has been just some sort of a DC shift happening over there. Now that is not unlikely. However, for some of them there has been a different varying nature of the shift which comes down, and over here you see that there has been a different shift in each of these color planes. Okay. Now, if you keep on running this over a longer period of time, as we had done in the earlier cases with just trying to use down convolutional networks of the very basic nature, you can actually see the trend setting in. And since we have just trained it down for 5 epochs for the sake of time within this video, it trains out, but you don't see such a major difference coming down over here. Now, if you set it running with learning update rules and over a longer number of epochs, maybe something like 100 epochs over there, and wait for some time, because each epoch for me is taking down about 25 seconds. So, for you it might vary based on whether you are using a CPU only or a GPU kind of a mechanism, but it's nonetheless one thing you need to remember is that these kind of mechanisms of using a deep neural network, they do consume a lot of time for training, and you will have to just wait and watch, nothing more than that. A good method, a really excellent one, but then the time consumed is also large. So, this ends up the first part of it, which is just with learning, looking into what representations it has learned. But then the objective of actually learning these representations was so that I can have a classification network which is very accurately initialized onto what features make up the data. Okay. Now, the next part is to modify this autoencoder part, which has a convolutional part over there, in order to make this into a classification network. So, what I technically do over here is that I define a newer kind of a model, which is just going to take down my initial part of the convolutional encoder and my fully connected part of the encoder, and then whatever is the resultant over there, which is 1024, just connect it down onto 10 classes over there via a linear connection. This is the only change which comes down, and due to this change you have your forward function also changed over here. Now, if your GPU is available, just convert it to the GPU, and then you can just copy your weights and keep it for your purpose. Now, we have a model which has already been trained and initialized to do a good amount of representation learning. What we are going to do over here is basically, so this is what your network looks like. So, you have your first part of it, which is just convolutional, the second part of it is the sequential, and the third part is what we are just now introducing in terms of a classification network. Okay. Now, we are going to train down this final classifier. So, whatever has been optimized earlier with an unsupervised mechanism, we are just going to retain all the weights over there and then do it. This will be trained over 5 iterations. So, let me just keep it running and then I can do the rest of the discussions. So, now over here if you look, so my optimizer is still Adam, not much of an issue. However, since my task has changed out and it now becomes a classification task, so the criterion function or the cost I use is a cross entropy loss. Okay. The rest of it stays as the same. However, over here for the first time I am going to make use of my labels. Earlier I was just going to make use of the image data for learning, but I never used labels over here since it is a supervised one in order to classify it into 10 classes. So, my labels comes for the first time. So, going down by what we have is you zero down your gradients, do a forward over the network, and then you are going to take a look into how good is the classification over there, and for that you have your outputs which are generated over there, that is the output for 10 neurons, and then you have your labels which are given down over here for comparison purposes. Now, once your loss is computed, you find out nabla of the loss or the gradient over that, and then iterate over the optimizer in each step, and that does your back propagation coming down. You calculate out your running losses over all the number of batches which work down over there, and then you can actually use that for the rest of the purpose. Now, following that, what we also try to do is, as we were doing in the earlier cases, is try to look down into how good has this network trained in order to do a classification process, and for that purpose what we do is we just try to take down data from my testing data set, which is independent. So, I have not used any of the data in my testing data set in order to train the whole network. So, I am just going to take that part of the data, and I just iterate it over all the samples on my test data loader, which I have defined it in the start of this whole code itself. And now, if my data is available, if my GPU is available, just get it converted onto your CUDA, and then the rest part is quite simple. So, you do a feed forward over this classification network, you get down whatever is your predicted index location which has the maximum probability which comes out, and then you see whether the predicted index is correct in terms of just matching it down, whether it matches down the label for that data or not. And then you normalize it over all the batches which are running down, and then you can just have a good look onto the whole thing by doing these two plots. So, one of them is going to plot down the loss in terms of classification learning, the other is going to do an independent accuracy of the estimation of the accuracy on the test data set which is available to you. So over here, this takes a lesser amount of time. As you see, it takes down about roughly 3 seconds in order to train the whole network, and that's quite common because in the earlier case it was taking more time, since you had the convolutional block which was there in the encoder. You had a convolution part of the connection in the decoder, and you had fully connected layers as well coming down. You have actually chopped it down significantly, and then we reduced some of the major costly operations which are in terms of using bilinear interpolation to upsample it out. Now, if you had just linear interpolations over there or nearest neighbor interpolations, it's much easier and a less costly operation. So these are places where just by introducing some changes, or by in case you accidentally take a ineffective mechanism, you are just going to increase the total time complexity over there. So the moment you changed it out, because the rest of the downsampling is something which happens in a much smaller time than the amount of time needed to do a bilinear interpolation over there. Now, from there we look into it that your loss, which was maintained in terms of cross entropy, it starts somewhere around 1.66, and then it goes down at the end of 50 epoch to 1.04. There hasn't been much of a change to say practically, and then looking at the trend of this curve, keep it running for 100 epochs, it would definitely hit down a saturation and a much better accuracy. Now, if you look into the accuracy part over there, it starts somewhere very low at about 38 point some percentages, and then at the end of it, it goes down quite high to about 56%. Now, not an impressive figure, but definitely there is a factor of about 20%, 18% roughly is an increase which you get down just by training it for 5 epochs. Now, if your initialization in the earlier case, say you had kept your autoencoder training over 100 epochs, and whatever you had initialized, you use the same thing for this classification over here, you would have started with a much higher accuracy because your features are much better. So it's in the same line as we had learnt out with our standard autoencoders in the fully connected mechanism. The same kind of concepts of learning and then better initializations do have a benefit cumulatively transferred over here as well. Now, once that part is done, let's look into the weights which come down at the end of this process. So these were the weights which come down after the end of this whole training process over there. Okay. Now, if I look down over here, so you would be able to see down your weight updates which come down. Now, you can see pretty much these weights updates are where you see a change in color coming down, and this was happening because one phase of it was just trying to represent the data itself, but the next phase is to get down more and more better kernels which are better for classification. So some of these kernels which were redundant in a sense that whatever be the class of the object, it would always be firing up in the same way. They are the ones which get modified to the maximum extent in order to increase your accuracy over there. So just these are for your own understanding, and then how you would be getting it done over all the other sorts of data coming down for your work. Now, the next part is what we strive to look into the performance of classification of each of these classes. So now there were 10 classes which ranged across plane, car, bird, cat, and then this is the average kind of a performance which goes down. You see that frogs get classified in the best possible accuracy. Deer has the worst accuracy coming down over here. Cat has a tad better than the deer, but most likely it might be confusing all cats with deers, and that's pretty much okay because it's a small sized image over there of size 32 cross 32. Now, this is just to give you the connections and then how we are going to make use of even unsupervised learning as in autoencoders within trying to get down a convolutional network as well. So, in the next classes when we get into more deeper convolutional practical networks like VGG nets and others, you can still use these kind of similar convolutional encoder decoder networks in order to initially train them, though they are typically not trained in that way given the computational complexity. So, just keep on waiting for the next lectures, and till then, goodbye.